So a little bit of announcement first. There will be a remedial session this Friday, as usual, SR10, 3 to 5. Okay, so I'll post the doodle later so that you can kind of vote on what, so you can give insight on what kind of topics you want to go through. All right. Assignment 2 should be released by 4:05, I believe. There's a password, and the password is that. I will post the PDF of the questions later so you can see as a PDF as well. Attempt it in Exemplify. There's one bonus question, which is question 0, but you need to open Exemplify first, right? So question 0 is just to check whether you can use PSQL together with Exemplify. Last semester we had no problem with this. However, I heard from CS1010E that they cannot run idle. Some students cannot run idle when Exemplify is running. So yeah, total mark is 4.5, but I'm going to round it down to 4. So 4.5 includes the bonus questions. There are 9 questions, including the bonus question. If you suspend, so I'm allowing you to suspend your attempt. The maximum time is 1,000 hours, I think. I forget whether it's hours or minutes, but it's 1,000. Okay, that's the maximum that I can give. If you leave your computer running while you're sleeping, then the timer will continue, right? So you can actually close Exemplify and suspend your attempt. If you do that, there is a resume code. Okay, all passwords and codes are, I believe, case sensitive. Okay, so midterm assessment, as I say in the announcement, is 5th of October. It's, I forget the name, it's UTown Auditorium 2. I know that there's a clash with CS24T, so if you're taking CS24T, please go for CS24T. I will arrange for makeup midterm. If you have other things, please email me as well. So I will only accept valid reasons, okay? And if you cannot come on that day and you're sick, please take MC. Okay, so that's the announcement. Let's go through quickly about the n-ary relationship. So let's forget about the terminology about like many-to-many, one-to-many, and so on. You should try to focus on how many of the entity can be involved in a relationship. Okay, so if you have two entity sets involved in a relationship set like this, so if you have something like this, and the line is kind of anything here, so this is an abstraction of any kind of line, then just ask yourself whether you allow 0, whether you allow 1, whether you allow more than 1. Okay? The one thing that you need to take note of is that every pair, for this particular instance, every pair of E1 and E2 will be unique. Regardless of what kind of constraints you are using, every pair of E1 and E2 will be unique. That's why if you look at it, question 3, if you answer it, it will always appear as no. And if you go for the n-ary relationship like the ternary, the triples will be unique. Okay, so let's have an example. Without any constraint, this is what we call a many-to-many. So every student can appear greater than or equals to 0. Within this relationship, every course can appear greater than or equals to 0 within this relationship. There's a few other things that is kind of implicit in this case because for this mini lecture, I'm only going to talk about the relationship. But it must also follow the rule that this must be an entity set by itself. What it means is that this is the super key, or the primary key. The CID must uniquely identify any other attributes. Okay? So that's implicit because this is an entity set. So if you have this explanation and then you ask yourself the 5 questions before, you appear at this answer. Okay, so notice that question 3 is always no. All right? And if you look at the key constraint, the key constraint, it must be less than or equals to 1. But because there is an implicit notion that this one must be an entity set, SID must uniquely identify the rest. Which means you allow for 0 students to appear in the supervisors. You allow that student need not appear in this relationship. And how do we do that? Well, there are a few ways, but it means that you allow a student not to have a supervisor. Okay? The relevant question has been highlighted in the same color, which is orange here. This one will be no. Because remember, this is at most 1. Okay, the same student cannot be supervised by a different professor. For a total constraint, total participation constraint, greater than or equals to 1. Okay, so the relevant question is this. It is no. Every student must appear in the enroll relationship. Okay? So this way, we can actually generalize this to the ternary. But before that, let's look at the total and participation constraint. You have both of them here. What it means, the relevant questions both becomes no. The orange is for the key constraint. The blue is for the total participation constraint. If you generalize this to ternary, then you ask for each of those entity or entity sets and each of the possible triples. This one, which is a generalization of the previous question 3, will always be no. You cannot have the same triples appearing twice. Right? So if you look at this, the professor can only appear at most once. Okay, so if you want to answer the question, then the same prof cannot appear multiple times. Anything involving the same professor cannot appear multiple times. Okay, so that is the orange, but there's also 2 other constraints that is going to be that will be no. In this case, is this, because it involves the same professors again. All right. So I didn't mark that as orange because it is kind of implicit in that sense. Okay, so if you involve a total constraint like this, then that appears as blue. Okay, so the first 3 questions here are for total constraints. The 4th question for the n-ary will always be no. And this one is for the key constraint of the professors, and these 2 are also the same key constraint. All right? So this one, again, less than or equals to 1. less than or equals to 1. This 6 or 5 are for that key constraint. But notice that these two cannot be yes as well, because again you have the same professor here and then you have the same department here. Okay, what it also means is that this particular diagram is actually exactly the same as this. Right? Let me draw the triangle. Wrong. Pen. These two are the same. Okay? So any questions? So yeah, so for simplicity, we will not have more than one different arrow. Okay, so which means that at most one key constraint or one total constraint. We will not have this arrow, which is key and total constraint. Okay, just for simplicity. So yeah, so any questions on that? So yeah, so the main thing here is try to forget about the terminology, like many to many, many to one to many, or one to one. Just look at the constraints itself from the point of view of the entity sets. Okay, so let's continue on the part 2 of the lecture 4, which is transforming our ER diagram into the SQL code. So these are the summary of the constraints. And what we're going to do now is to convert from the ER diagram to SQL. Okay, so simple case first. How do we create an entity set? Okay? Every entity set will be a table, at least one table. And we have this. We have a student here. So we have a student here. All you have to do is create that student table. Okay? And the primary key, just declare them as primary key. Okay, so pretty straightforward. The domain is kind of up to you, unless the question stated it. Most of the time, we will just possibly allow just integers. Okay, we are not really that strict on the domain, except for your project. In your project, you must follow a kind of a real-world example. So name cannot be an integer. Okay, so for an entity set with multiple primary key, you use this. Just list everything as the primary key. Okay, so that is highlighted with the orange color here. If you have candidate keys, like we said before, candidate key can be captured by the not now and unique constraints. The primary key is always underlined, which is over here. So that's a primary key, and this is written in a column constraint. You can also write it as a table constraint down here. So primary key, office ID. All right. For the candidate keys, specify them as not null and unique. All right. So that's the highlighting. The blue is the candidate keys. There is no keyword called candidate keys. So you need to do the not null and constraint. So this one, the keyword does not exist. The keyword that exists are primary key and foreign key. Okay, so that's basically entity sets. So what about relationship sets? Okay, so we start with the simplest one, no constraints at all. Then the simplest way to actually create this is basically a table by itself. And what you need to note is that, so this is your table name and roles. For any value to exist there, you must connect the two entity sets. These two entity sets must be connected. All right? For them to be connected, then you have to make sure that they both exist. For them to exist, you use a foreign key. So these two are foreign key constraints. All right? Now the last one is that you do not want to have an unnecessary entry. What I mean by unnecessary entry is that a student without any course should not even be listed as an entry. But it is possible if you do not have the primary key. Right? If you do not have the primary key, what can happen is that you can have a student with an SID of 1 and the course null. Okay, what it means is that that student actually does not have a course. If a student does not have a course, then the grade here is useless, right? But this one means that you can actually create something like 1 null 5.0, which is an erroneous entry. To prevent that, if it appears here, it must appear without any null values on the two foreign key that we reference. All right? And the other thing is that this ensures that a duplicate pair cannot exist. Because again, a primary key is one of the candidate keys that we select. That means primary key must also satisfy not null and unique. Okay? So a student cannot enroll to the same course twice. Okay, and this are the highlighting. The grade here, which is the attribute of the relationship, appears only here. Okay? And the one in orange means that those are the primary keys of the respective entities. Okay, so that's actually the simplest kind of relationship set that we can construct because we don't have any constraint. Once we introduce constraint, we may actually reduce the number of tables. Okay? But before that, let's look at how does ternary relationships captured. So this is a ternary relationships. So you have 3 entity sets. Over here is basically just being referenced. The 3 of them are being referenced. And we only need to store their primary keys. All right? So any questions so far? One thing that I haven't really talked about is what happens if one of the entity sets actually has multiple primary keys. Okay, so let's say the project ID and the budget are actually both primary keys. Now, how do you capture that? Okay, so basically, just add the budget over here. So this one, we cannot use this kind of foreign key. We just add the budget. And then for the foreign key constraint, we capture it outside using the table constraint. So you have foreign key the pair, which is PJID and budget, that references both of them. Right? So yeah, so any questions? So now so this is the coloring. We look at what happens if there is constraint. So this is a key constraint. Oh, actually, before that, let's do a demo. I forget that I have uploaded SQL, lecture 4 SQL. Okay, so we start with out any relations. I can create a student table over here. Okay, so now there is a table. I can do some kind of testing. If I try to insert a value with a duplicate primary key, it will be rejected. So this one is going to be rejected because the student ID already exists. But if I try to insert values where the student ID does not exist, it will be accepted. So now if I query, I will get this. Okay? So Office is about the same. This one is if you have candidate keys. So let's insert this one first. Okay, so this one, the primary key is the Office ID. So if you insert something with the same primary key, but all the rest of the values are different, then you will get an error. Okay, and similarly, if you have the building and the room to be the same, but you just give it a different primary key, it will also not going to be accepted. All right? And yeah, this one, the details is that it violates the unique constraint. Okay, so for enrolls, you need the core, so just copy all of this. What we are going to simulate is this one. So insert something first. And we can now insert into the enrolls. And if you query from the enrolls, what you will see is this. The student with the student ID 1 is enrolled in 2102, and he's also enrolled in 1101. The same student cannot be enrolled in, so student ID 1 cannot be enrolled in 2102 or 1101 again. So if you try to insert this, with a different grade, you will get rejected. Okay? So that's the question number 3, which is, can the pair exist more than one? So the answer is no. And this is the same again for the multiple arity. So this is the ternary relationship. You just have to insert more values, and then this is what you will get. Okay, so far I'm only putting in one supplier, but with a different parts and different projects. Okay, so any questions? So if you look at this now, for the key constraints, if you have a key constraint, remember that the constraint is the student can only appear at most one within this relationship. So how do we enforce this? Okay, the way to enforce this is actually a few ways. The first approach is to use a separate table. But how is this different from the previous one? This is different from the previous one in the sense that this SID is the only primary key. For the previous one, we have SID and PID. Okay, which means that you can have a pair. So you can ask yourself this question. Right. Can the same student be supervised by different professors? Okay, so I need some kind of drawing. So let's wait a little while first. So the question was, can the same student with the same SID be supervised by different professors? So what it means is that, can I have this? Can I have SID and PID1 with SID and PID2? Okay? If this is allowed, that means the constraint, this ER diagram is not captured. The constraint is not captured. And this is not allowed in this particular instance because for the first approach, we know that SID is a primary key, which means this duplication is going to be rejected. Okay, and similarly for this one, if we combine it and SID is still the primary key, the only primary key, then this will be rejected as well. But let's ask a different question now. Can we have a student without a supervisor? In this case, it is simple. You just no need to actually put it inside this table at all. Okay? If it doesn't appear there, if the entry does not appear in the supervisors, that means that student is not being supervised. But here, every student must appear in the supervised students. You cannot have a student that does not appear here. So the only way for a student not to have a supervisor is if you have an entry SID null. Okay? And we need to allow this. And because we need to allow this, transforming from the schema to the SQL is basically just allowing the PID here to stay null. So now you can have a student without any supervisor within this single table. And the way to do that is basically letting the PID to be null. For this approach, if you want a student not to be supervised by any professors, then what you need to do is you need to make sure that the entry does not exist, that the SID does not appear anywhere here. All right, there's a subtle difference between the two approaches. Okay, so before we go to the demo, to show that this actually works, let's take a look at a key and total constraint. So I'm going to skip total constraint only. Let's look at key and total constraint. For a key and total constraint, this one must be exactly 1. Okay? So now let's try the two approach again. The only difference now for the second approach is that every student must have a supervisor. Okay? If every student must have a supervisor, this one cannot be null. Okay, so that's the only thing you need to reject. So now this one is not allowed at all. Every SID must have a corresponding PID. But if you look at this, SQL, look at this table, what's going to happen is that the total constraint is not actually going to be captured. And the reason why it's not captured is because you are not enforcing that every student, every SID must appear here. You can have that table empty. If you have never inserted anything, you can have that table empty. So if you want to use this approach, the first approach, then you need to control the total constraint in another way. If you created the ER diagram with this second approach, then the total constraint is actually captured. This one, the first approach, does not capture the total constraint. And to capture it, you need a different approach. Okay, so this one is basically, there's no, the total constraint is not captured. Okay, for the first approach. So let's look at the demo. So I need the professors and the students. So the professors are the same all the time. So this is still on the key constraint only. Okay, so let's take a look at the professors table first. So this is only one professors. And then for this is the first approach. So if you want to insert something, yeah, this one cannot be inserted because it's the same SID, okay? Which means that the key constraint is actually captured. Okay, because the second one here has the same SID. Okay, so SID with a different PID, the same SID with a different PID cannot be inserted. And if you query the table, this is what you will get. This is the only students that is being supervised. And it is being supervised by the PID 1. And the student that is being supervised is this. All right? So any questions? So let's try the second approach. Actually, you can also check the students that are not going to be supervised. These are the students. Okay. Later on, we will learn how to create a query that captures exactly this. For the second approach, we create a combined table. So we don't need the student table anymore. So I can actually drop that. I can drop this. I can drop table if exists students. Oh, enrolls is drop table if exists, enrolls, and students. Still the same. Okay. Okay. Right. So now I don't have students and I don't have a lot of things. Okay, so I do have a supervised student. So if I insert this, the first one, the student ID is 1, so it's just going to accept it. Right, so that's one student, and the student is supervised by the professor. If I insert the same student, but the student is going to be supervised by a different professor, then this one is not going to be allowed. Okay, so key constraint is captured. This one is also not going to be allowed. You cannot insert a student that doesn't have any supervisor, but it's not included because this one is still 1. Right? So you do not have that what we call as an entry that is conflicting, because one of the entries that we already have is that this student with this SID is already supervised. So if you insert it again, that this student, but this one is null, it is not going to be allowed because there's a conflict. However, for the rest of the students that does not have any supervisors, they must have a different SID. So then we can look at this. So from here, you can clearly see that there's only one student that is being supervised. And you know that because the PID is not null. Okay? And we also allow a different professors to actually, the same professors to actually supervise different students. And we can update table supervised students, set PID equals to 1. So everyone is currently being without the table. Okay? So everyone is being supervised, except that the since value is kind of erroneous here. Okay? But what we're concerned now is just with respect to the key and total constraints. Okay, so any questions on this? So the next one is that this is some textbook actually call this a recursive relationship, where the same table appears twice in that relationship. So the same entity appears twice in the relationship set. Or you can also think of it as a one array. So one array, or some textbook actually put it as recursive. Okay, so if you want to have a role here, then the way you can enforce it is that by naming it. You create a different table for the relationship set. You cannot just combine them. So this is the mentors, and then you just give it a different name, right? And then just reference the same table. Okay? So any questions? Now, if this one has a key constraint, then you may actually collapse that into one table. Okay? Because again, following the second approach, you can collapse that table. Okay, but this is one way to actually capture the necessary constraints. So I'm going to skip this demo for this because it's quite straightforward. The next one that I'm going to show you is this, the weak entity sets. There is a subtle thing here. Remember when we said that this one, implicitly, it is still an entity set, which means that the ISBN will have to uniquely identify the rest of the attributes. This particular entity set is a weak entity set, which means that the num here cannot uniquely identify the title. Okay, that is based on the definition of the weak entity set. So what we will have is that although it looks similar to the second approach, the subtle difference here is here. The primary key for this combined table is not just going to be num, it's going to be both num and ISBN. Okay? What it means is that you can have duplicate num. Almost every textbook, or practically any textbook that I know of, have a chapter number 1. Okay? That can be duplicated. But a combined one, number and ISBN, can never be duplicated. Okay? And that's critical in the weak entity sets. The other thing that is important is this: on-delete cascade. What does it mean? On-delete cascade ensures that this chapter cannot exist independently. If you remove the book, you will remove all its chapters. All right? So that is something that is very, very critical. That chapter cannot exist without a book. So that's why if you delete the book, if you delete the ISBN, you have to delete the entry, all the entries that refers to that ISBN. Okay, so any questions so far? So if you look carefully over here, this is not going to be a table, but this, both of them, is definitely going to be a table, one single table. So yeah, that's a weak entity set. The next one is this other ER concepts that we haven't discussed that I'm going to introduce now, and one of them is based on what we call the superclass-subclass relationship. So if you study OOP, P, so remember that you have the superclass and the subclass, and the subclass is a superclass. So this is that kind of relationship being captured in a database. And we capture it using this triangle. So every undergrad is a student, every graduate student is a student. And then you can have relationships that is based only on the subclass, or relationship that is only based on the superclass. If it is based on the superclass, it means that both the undergrads and the grads must belong to that relationship. Right? So if I have this, enrolls in a course, that means an undergrad can be enrolled in a course, and a graduate student can also be enrolled in a course. Okay? But this particular part means that the undergrad cannot work. Only the graduate student can work. Okay, so that's the subclass-superclass relationships. And we have two constraints here. There is a generalization of the superclass-subclass. There's this thing called overlap. if you satisfy the overlap constraint, that means a particular instance here, a student here, can be both an undergrad and a graduate student. Okay? If it satisfies the overlap constraint. Okay, that is probably not allowed in OOP. At least in Java, that is probably not allowed. Okay? The other one is a covering constraint. The covering constraints means that every S here, every S in the student set, the student entity set, must appear in either this, or both. Okay? So S must be inside here, S must be inside here, or both. Okay, so that's covering constraint. Overlap constraint, that means this S can appear in both. Covering constraint means that every single S in the students must appear in at least one of them, one of the subclass. Okay? In general, overlap constraint cannot be enforced because it cannot be enforced without tricks. Okay, some of the tricks is basically the use of triggers. Triggers can allow you to maintain to capture constraints that belongs to multiple tables. If you think about it, the overlap constraints, or rather, yeah, the overlap constraint, right? If you say that the overlap constraint is not satisfied, the way to enforce that is you need to look at the undergrads table, you need to look at the grades table, you need to look at the intersection of them. The intersection must be empty. Okay? But you need to look at both. Because you need to look at multiple table. The table constraint is generally not enough unless you do several tricks. Okay? So I will show you some of the tricks using triggers in future lectures. Another way that you can do this is that you have a dummy attributes. A dummy attributes, you can say that, well, I have a type. You ensure that the type must be either undergrads or grads. And you can do that by using a table constraint. You can check that this is equals to undergrads or this is equals to grads. Okay? Now, when you are at this particular table, you need to have that type attribute as well. And the type attribute must refer to this type attributes. But this type attributes can only be undergrad. Okay? That ensures that the overlap constraint is not satisfied. Because you cannot put a graduate student there. So yeah, those are just some different tricks. But let's look at the simpler approach. The simpler approach is, without any kind of trickery, is this one. This table, this schema, is basically saying that for you to be an undergrad, your SID must exist over here. Okay? So that's why you references it. The references guarantee that the SID must appear in the students table. And secondly, if the student is being kicked out, so if the student is removed here, you also need to remove the student ID over here. And that is guaranteed by the onDelete cascade. Okay? So exactly the same thing for the grads table, but because of a space constraint, I exclude the bachelor degree. Now, if you say that the covering constraint is always satisfied, you can actually remove one of the table. Okay? So what it means is that you don't care about the superclass at all. What you care about is that every superclass must exist as either undergrads or grads. That is why you do not need to reference the student table. But if that student exists, that student must exist as either undergrads or grads. Okay? How do we construct back the student table? That will be through the use of union. If you union the two table, and then you project only on the SID before you do the union and the name, then you get back the student table. All right? What you also need to note is that all the attributes of the students here must appear in both the subclasses. Right? So this guarantees that if a student exists, the student must exist as either undergrads or grads, because it cannot exist as anything else. And if you want to combine those two to get back the student table, to find out who are all the students, then you need to use union. Right? So I will tell you how to use union later. And the last additional concept here is aggregation. Aggregation is something that is unique in a sense that most of our relationships involve two entity sets, right? Because if you think about it in terms of an OOP, you have two objects, and then you have a function that works on those two. This one is slightly different because you are connecting two relationships. Right? And what happens here is basically not that the monitors is relating between sponsors and employees. What it means is basically that the monitors is actually connecting between this aggregate entity. You think of them as one big single entity instead. Right? So an employee, so every project is sponsored by at least one department. So you need to create this aggregation, you need to satisfy each of the constraints inside. So this is at least one is captured here, okay, and so on. And then you also need to connect the monitors and the sponsors. The way to do this is, again, it is about the same. It's basically you kind of treat that sponsors as a big aggregate. You treat the sponsors as if it is an entity. Because it involves 5 sets. I'm going to show you the first 4 sets first. Okay, so you have a project, you have a department, you have the sponsors, and you have the employees. Right? And this already captures that big aggregation, as well as the employee table. Okay, what we haven't captured is just the monitors table. For the monitor table, what we do is we just connect it to the sponsors table. So it connects between the employees and the sponsors. It connects to the employees by using this. References this. And it connects to the sponsors by this one. Okay? So at this point, the sponsors is kind of treated as an aggregate entity. And yeah, so the rest is basically about the same. The primary key involves all the primary keys in all the tables involved. So this, and for the sponsors, the primary key of the sponsors was this and this. So any questions? Yes. Again? Well, to answer that is because in our design, the aggregate is on the sponsors. So that's again based on your design. But you know the aggregate. The aggregate is encompassing this. Right? Because the sponsors now becomes the aggregate of the two entities that it's relating. Yes. The aggregate must be specified with that bounding box. So yeah, this one has to be specified in your design. Some design also actually, so I'm not sure if you can see it here, but some design doesn't even have this line. That lower half of the line doesn't exist. Okay, so which means that it's kind of almost clear that this monitor is actually connecting to the entire aggregates. Okay, but this one is, I guess, the most common representation. Okay, so any questions? Right, so this is self-read and this is the summary. So let's have a quick 5-minute break before we continue with lecture 5. If you have the no, so again, this is never the only way, because you can always use triggers. Right. So this is never the only way. Triggers is basically typically it's used for constraints that spans multiple tables. Remember the covering and the overlap. If you want to enforce that the overlap constraint is not satisfied, you probably need to use triggers. The value here cannot exist over here. Because the student did not exist here. You have a student table. Right? The first approach is so the collection of the first approach was that you have a separate table. You basically have used a separate table, right? So this one means that you have a student table. But that means a value might exist in the student table but doesn't exist here. It exists here but doesn't exist here. No, it's not now, but it doesn't exist here. You just never insert it. Yes, but if you never insert that SID at all, then it doesn't exist here. Okay, so let's say I have this table, right? So student table. So student table that has an SID. So this is SID. I have 1 and 2. Then supervisors. SID, PID only have 2, then is student 1 being supervised or not? But is this one that is referencing this? It's not this one referencing this, right? So student 1 is not being supervised, and it does not get captured. That constraint does not get captured. Yes, it doesn't capture the total constraint. Yes, because you do not have this table at all. You merge these two tables. So every student must exist. Yeah. So primary key here just ensures that the SID can never have a duplicate. The foreign key means that the SID must exist somewhere on the other table. That's it. Yes. So primary key says that the primary key says that this value must exist as a non-null value, and it must be unique. The foreign key says that this value must exist in that other table. That's it. Yeah, because the line here doesn't have any constraints. Yes. No, so I cannot mentor the same student multiple times. It's the pair that is unique. If there's an error, then you need to look at which one must be unique, which one must be not null. Yes. The what? Mm-hmm. No, this is partial. Partial means that there is no constraint. Total means that there is constraint. Yes. There is a kind of constraint here because every triple must appear exactly once. No, every triple can only appear at most once. That's the constraint of that relationship. Yes. Yes. Yeah. So this one is basically there's no key constraint, there's no participation constraint, or we can say it's a partial participation constraint. Yes. It's the same type as whatever you declare. No, but you declare what is the type, right? And that if it's a foreign key. Uh-huh. Uh-huh. Yeah, it's a null value. Null value can be of any type. Yeah. It is not considered not null. Yes. It's unknown, right? So it's a three value logic. So I cannot answer your question because it's unknown. So what it is considered is it's not considered as not null. Right. Because the opposite is not necessarily true. Huh? No, because when you want to check for constraint, for let's say a foreign key constraint, it must be not null, or it must appear as a primary key in other table, right? So what I can only say is that if you have a pair and that pair references something else, and one of the value is null, I can say that it's not null. Huh? You cannot use it as a key or candidate key. That means it's definitely not declared as a candidate key. Okay, so let's talk more about SQL queries. We look at the more advanced kind of SQL queries. So 2 lectures ago was a simple kind. So this just for your revision. What we want to do is, for the more advanced one, we have pattern matching. We have conditional expression, which involve either case analysis or a null analysis. The basic for these conditions is that the conditions appear in the where clause. Okay, so this is the only place that it's going to appear. And we have many different syntax. So the syntax for pattern matching is like, for case analysis, you have case something and. For the null analysis, you have 2 different kind of keywords. It's a null if and coalesce. Like here is actually not regular expression. It is simpler than regular expression. If you want regular expression, you can look it up online. There is actually a pattern matching that uses regular expression. However, I'm not going to bother you much with it unless you want to use it for your project. It's fine. For the like, we have simple rules. So you can have this kind of syntax. The attribute is like this pattern. And when you try to match things, you have 2 very special characters, which is the underscore, which match exactly any one single characters, or a %, which match 0 or more any characters. Okay, so if you look at this example, any other characters is treated as they are, as it is. A must match with A, B must match with B, C must match with C. So if you use like, but you do not use any of the special characters, it's basically equality. Okay, so the first one is definitely true. The second one, A is going to match with A, B and C is going to match with %. Because % match 0 or more. So this one is fine. Okay, so ABC here also match with underscore B underscore, because the first underscore match with A, the last underscore match with C. Only this one is not going to match, because A is going to match with with C, and that's going to give you false. Right, so that's the mapping. So we can have interesting questions such as, find all customers ending with E that consists of at least 4 characters. The white space there is just for you to see. There should not be any white space. Okay? So yeah, so you match at least 3 characters. The 4th character is definitely going to be matched with E. But any other characters, you can include it right before the E. Okay, so this one definitely going to answer the question. So let's try this. Find all customers with a name starting with M and ending with E. So you have Mo and Maggie. Okay, so this, well, definitely you must have an M, right? And also definitely you must have E. Anything in between can be as many characters or as few characters as possible, so you use this. Okay, so that's this again, the white spaces are just for your visual. Okay, so that's pattern matching, pretty straightforward. Conditional expression is basically like an if-else statement. Okay, so it's not just if-else, it's if and else if. So the first one here is your if. Any subsequent when here will be your else if. Which means if the first when is already satisfied, you will just take this result immediately. The second when is allowed to satisfy the first one as well. So what it means is basically something like this. You have 4 cases. This is not the cutoff grade yet for this module, so you are still safe. But let's say this is the case. If you get 85 or more, you get A. If you get 75 or more, you get B, and so on. So what you need to do here is this one is greater than 85. For the second one, you do not have to check that it must be less than 85. You can simply check that it's greater than or equals to 75. So that's what I meant when I say that the second one and any subsequent when is treated as an else if. It is only going to be checked if it doesn't match the first one. Okay, so this is what it's going to look like. The else is going to match any other case. Which brings us to the question, what happens if it doesn't match any and we don't have else? What will be the value? Null, correct. Okay, so if you want to have null, then you can do this. So this is a null analysis. If it's absent, if the student is absent, the student is neither pass nor fail. Right? So if I say that this one is pass and this one is fail, if it doesn't match any of this, it will be null, which is exactly this. Okay, so if you convert that, you will get something like this. If the result is either pass or the result is fail, then you take the result. Otherwise, it becomes null. Now, we only have 3 cases here: pass, fail, or null. Right? If you have more cases, it will be more complicated. So we can actually simplify this by using a null if operator. The null if works this way. If the result is absent, then it is null. Otherwise, it is the result. Okay? So you match the result with absent, with what should be the null value. If it is that, then you basically put it as null. All right? So that's a null if operator. The second one is actually more complex here. We want to know if a student pass. A student pass, so a student have 3 attempts at any single quiz. A student pass if we give him a pass grade, and they cannot attempt any further quizzes. If a student fail or student is absent, we allow the student to have another try until at most 3 tries. What we want to get is that we want to get the first pass from the left or from the right. Okay. So Alice here already passed. She cannot do the question again, the quiz again, and we say she passed. You only fail if you absent on all or you fail on all. So if you write it down explicitly, what you will get is if the first is passed, or the second is passed, or the third is passed. For any other cases, you get fail, including null. All right? But this one is actually going to be very, very tedious if you have n attempts. Okay, if you have 200 attempts, the code here will be very, very long. Okay? What we can do here is we can coalesce the values such that you take a series of arguments. Based on this series of arguments, you take the first value that is not null. If you have this one as null, this one as a pass, and this one as fail, then you take this one. Okay? Which means that there's a question here, that's the order method. The answer is yes. If you check the first before the third, and the first already fails, even though the second attempt is passed, you will get fail. Okay, so if this one, if we invert the order, so this one is first, second, third, and we have this one as fail, pass, null, what you will get is fail. You will get the first non-null values. So in this case, yes, the order matters. Okay, so any questions on this? So we can look at some of the next one. We will stop at the set operations, or set and cross product. Next week, we will continue with the join. Actually, we will see if we can actually cover this fast enough. For the set operation, it's actually very, very straightforward because there is a mapping, a direct mapping. If you want to do a union, it's just union. If you want to do an intersection, it's intersect. If you want to do a set difference, the keyword is except. And again, remember that in our case, when we talk about relational algebra, when we do any of these operations, the result is a relation, and we define a relation as a set. The set should not contain any duplicates. So if you use this, all the duplicates will be gone. If you want to keep the duplicates, then you have to use all. Okay, and this gives a very interesting cases. Okay, so this is some of the possible use case. You can read it on your own. This gives a very interesting case. If you look at this, if you use the all, for some reason you then get 1. But 1 is not present in here at all. So why is this so? Okay, so you remove, we first do a projection here. You do projection on B, we do projection on the attribute D. If you do the projection, this is removed. If you say except all, you keep everything first, right? Which means that there are 3 cases of ones. But there's only 1 cases of ones. So this 1 cases, this singular cases, will only remove 1 of them. All right? That's why you get the 2 ones over here. The 2s and the 3, this one is going to be removed by either this or this. It doesn't really matter. This one is going to be removed by this. 4 is not going to be removed at all. Okay? So there's one slightly interesting behavior here. And you need to be very, very careful with this. The cross product, we actually have already discussed. This is the part where the cross product is used, and this maps to the from clause. So if you want to do a cross product, you basically just have to state all the tables, all the relationships within the from clause. And for it to be valid, you must be able to identify the attributes. And to be able to identify the attributes, either you do a renaming if there are duplicate attributes, or what you need to do is you need to use the dot notation. There's an area here, so we do customer.area and restaurant.area. What it also means is that you cannot do a cross product on the same table. You cannot say customer, customer without doing any renaming at all. If you want to do any renaming, the keyword was as, right? But in the from clause, you can actually exclude that keyword. If you give customers C, that C is treated as if it's a renaming of customers. Okay, so SQL is actually trying to be permissive. Now, last one is that if you have conjunction or disjunction in your condition, so and or, you need to specify it here. Okay, actually need not be there. It can be and here. Okay, I'm just specifying it there so it can easily it is easily readable. Okay, but conjunction and disjunction can be specified as either and or. Actually, let's try to continue with the join. We do have some time because I think the next class is usually come at around 35, 40. We have multiple kinds of join. Right? Join is kind of like a cross product, but you can specify certain conditions, which means that you can combine the cross product together with the selection. And you can also do some kind of projection. But the projection is only for the natural join. The inner join, you have actually learned about this. The inner join is basically just a cross product with selection. There's nothing new about inner join. So if you are doing something like this, you have a cross product with a condition, with a selection. You can actually combine them here. And you can write it as a single SQL query. So this is for the cross product. For the inner join, you write it as from something, inner join something else. You specifically say that you want to perform an inner join, and then the inner join must satisfy a condition. The condition is specified with the on keyword. That's how you perform the join. All right? So if you perform the inner join is on this constraint. This constraint match exactly the condition C. Okay, if you do not want to use inner join, it's up to you because you can always use the cross product. So that's inner join. Inner join is the standard join. So if you don't put inner, you just say join, is the same. Join is just an alias for inner join. Notice that we have this thing called dangling pointers. Remember that you have the conditions, right? If the condition is not satisfied, that means that particular row will not be involved in the join. That's what we call as a dangling tuple. Okay, not dangling pointer, it's a dangling tuple. It does not satisfy the condition C. In this particular case, this 2 in the middle and this one are the dangling tuples. They do not get used in the final result. To preserve the dangling pointers, you have to use the outer join. So those are the dangling pointers. There are 4 kinds of outer joins. There are left outer joins, the right outer joins, and the full outer joins. So simplistically, this is what you will get. The left outer join is basically an arrow from the left to the right. What it means is you preserve the dangling tuple on the left. But because it doesn't have a corresponding value on the right, you make them null. The right outer join is an arrow from right to left. You keep the dangling tuple on the right table, and for all the values in the left table, it becomes null. Okay, so that's what you get. So you keep this value, you keep this dangling tuple, this value will become null. For the right outer join, you keep this dangling tuple, this part is null. The full outer join preserve all the dangling tuple. You may have seen diagrams online that is doing something like this. So you have R and S. Left outer join is this. Okay? If you are not sure what that means, let me tell you what it means. This one is everything that satisfies the condition. Okay, so you have the condition C. This middle part satisfies C, which means that this one is the dangling tuple from the left relations, and this one is a dangling tuple from the right relations. Left outer join preserve the dangling tuple from the left. Right outer join preserve the dangling tuple from here. Full outer join preserve the dangling tuple from both. So that's what the diagram meant. The diagram will be duplicated at the end of the slide. Again, this is actually just definitions. I'm not going to test you on this. This is how we arrive at the left and the right outer join. But you get the intuitions. The intuition is that you have a dangling tuple that does not get selected in the selection clause, the condition. You want to preserve that. And to preserve that, you need a way, you need an operation to actually get that. And this is actually just an explanation on how to get that. Okay, so this is actually skippable. So this operator gets all the dangling tuple. And we can get that. This one is the dangling tuple. This one is all the null values. You want to combine those two with the inner join. Okay? So left outer join is an inner join plus all the dangling tuples from the left. But before you can do a union on them, they must be union compatible. To make them union compatible, you just do a cross product. So now these two are union compatible, you can union them. And this is just an example. So you have this is the dangling pointer from before. This is a set of null. Once you perform a cross product, this is what you will get. This is exactly the dangling tuple from the left relations. Okay, so the right outer join is also the same. Is the inner join union with the dangling tuple from the right. This is just an example. The interesting thing is the outer join. You can have multiple definitions. Because we work in terms of set. You can actually union left outer join and right outer join. If you union them, you get the full outer join. Or you can use the definition of the dangling tuple union with the outer join. Okay? Dangling tuple, right outer join. Or you can just use a union from both dangling tuple. So yeah, so that's basically outer join. We'll go through the example next week. The last one is actually natural join. Natural join is a special case of inner join. Remember that in the inner join, you have to specify the condition. In the natural join, the condition is going to be inferred. It is going to be inferred by if you have attributes that have the same name in both tables, you will use that as an equality check. So let's go directly into an example. Take a look at this. You have relations R and you have relation S. D is duplicated. Attribute D exists on both tables. Attribute A exists on both tables. When you do a natural join, what you will do is say that R dot A is equals to S dot A, and R dot D is equals to S dot D. Because those are attributes that are the same on both tables. Okay? So it's implicit, the condition is implicit. The other thing is that you are also going to do a projection, because these are going to be the same. Right? Rather than having a duplicate attributes, you just remove one of them. And you can do that safely because the two values are always going to be the same. Why? Because we do a check, an equality check exactly on that attributes. So you can remove them through a projection. So that's a natural join. And that's basically all the joins that we have. All right, so any questions? So let me show you the summary. Views is for next week. This is the summary, and this is the summary that I told you before. This is your left join. Left join is basically left outer join. Right join is right outer join. This is your inner join. And this is your full outer join. Okay, so those are what you probably need to remember. Okay, so any questions? Okay, so if there's no questions, then I'll see you next week. Uh-huh. You can interpret it in many ways. So template can be like it's basically template like it must have name, it must have something, it must have something. But you can always add other things. But as much as possible, if you have that in the UI, you must have you should probably have the database that captures that, and that database ideally should be consistent regardless of who is using the database. So which means that the constraint, try not to enforce the constraint only on the UI. So, but try to capture the constraint on the database itself. No. So I mean, so the project must have a name. A project must have members, and so that's a template. So you must have a page that displays that this must be the thing that you fill in. Then, if you want something that is more complex, you can say that you're allowed to have, say, like fields like keywords, and the keywords can be many. So how do you capture that? Because it can be many. It can be 0 or more. So, but the template must have this, and then for certain things, you can have more. So think of a template as if like a web page itself. But no need. Yes. Natural join is a special kind of join. Yeah. Where.
What do you mean with in the join there's a condition, but
yes.
Natural join is a input condition.
Yes, because the database, the DBMS know which of the two tables you want to join in a natural way. Yeah. And the most natural way to join two tables is that you look at the attributes of this table, you look at the attributes of this table. The subset of attributes that appear on both must be equal.
Must be equal.
Yes. You
say that it's equal, exactly equal. So this is common attributes. So you get all the attributes from R, you get all the attributes from S,
Yeah.
you do an intersection of them, that's how you get the common attributes.
The common attributes would be like D and
D,
E.
A, and A. So D must be, D over here must be equal to D over here, and A over here must be equal to A.
But how would they know? Let's say, like in our previous example, this is like called SID, but this is called student ID.
No, then they won't know.
They won't know. They must be the exact same.
Yes.
Alright, okay. Thank you very much. Yes.
If you can, yes. So, especially for constraints, right? So, think about it this way: your constraint, your table, your database, can be used by anyone. Let's say you want to open your app to everyone to create an app for you. You want to open your database so that everyone can make an app. That means your database itself must be consistent. Anyone who uses it will not be able to screw it up. No, no need. It depends on what kind of permission. If the permission is part of the project, then yes, you have to implement that. But if what you're meant is basically a permission to connect to the database, then no. No, then that is must be captured by it's probably cannot be captured by the database constructor. But you can capture it by SQL queries. So again, yeah, that one only can be captured. Because that one really cannot be captured by any database constructor. Not even Qt. Actually, you can. In a way, you can. Because you can always create a view, and that view can always be SQL. But no need to go with that. And if you cannot do it, explain